Hello, my name is Vlad. In this presentation I would like to discuss the topic improvement of the end-to-end encryption algorithm for web messenger system. The messenger system with end-to-end encryption, which provides data protection from the server, does not provide the same protection today because due to the large number of messages transmitted in one session using session encryption between user and server, their protection decreased. Because session encryption ceases to be unique and turns into a simple double encryption, the alternative to which is a more profitable increase in the key per byte. Of course, this can be solved by increasing the size of the keys, but such a solution will put a lot of strain on the server processors. Because encryption large messenger will be a rather heavy processor, and it will not look rational with small number of transmission messages. So now they just trying to find a compromise between key length and encryption speed, or not to use session encryption at all. Since it is impossible to crack modern encryption standards with current technology, but in the 30-40 years it may be processed to crack it. For example, if 256-bit ISK can be cracked in a year. And if a larger number of messages are intercepted in one session, it will take 2 years to decrypt them. All messages will be decrypted. Encryption through the server is usually implement a session encryption between the client and the server, which provides unique encryption for each session but make user data available to the server owner. The second scheme is end-to-end encryption, the essence to which is that encryption and decryption are performed only on the parties, sides and server only transmitting them. Uh, To implement end-to-end encryption, users need to pass their public keys to the server. Then the server can request the recipient public key. After the encryption process to the encrypted message is sent to the server, and then the recipient can ask the server for his messenger and the sender's public key. Usually, end-to-end encryption is used in conjunction with session encryption to provide additional data protection when transferring data between the client side to the application and the server. Since session encryption is always performed with naively generated session key, this gives each connection double protection during data transmitted, where the top layer of session protection is unique. Therefore, even if an attacker first discovered the recipient's secret key, they will not be able to decrypt the message. But the strength of session encryption for each message decreases with each. Additionally, messages therefore when a user receives a large number of messages encrypted with the same session key in one session, the strength of the encryption decreases because if an attacker intercepted, then he will only need to decrypt one messenger at the same time. All the other messages intercepted during the session will become available to him. To solve this problem is a process to encrypt each message with additionally new key that will encrypt only it. So an attacker will need to crack each message separately, which is transmitted during the session. This makes it almost impossible to decrypt all messages during the user lifetime. Also, by implement end-to-end encryption on elliptic curves ESS, whose key-bit encryption is based on the Diffie-Hellman SDH scheme whereby the secret key of one party and the public key of the other agree on a common secret from which they generate a symmetric key. Also, the public keys of an SDH messenger will be transmitted using session encryption, so an attacker cannot ever try to calculate the user key from it. The author also suggests that the server should not decrypt messenger with their special key upon recipient from the sender, but rather transfer the decryption to the client. To do this, the symmetric message key should be stored in the database with the message, and only the key, not the message itself, should be encrypted when it is sent to the recipient. The advantage for the server is that it does not need to decrypt larger messages upon recipient and decrypting them for transmission to recipient. Only a small key needs to be encrypted. With modern security standards for iOS, with the crypt block chain mode, which requires encryption each block using the previous one, it is not possible to process it in many tricks. So each increase in messenger size leads to coordinate increasing in encryption time. So a 256-bit key is encrypted with a key of the same size in 0.003 seconds, and an 8 megabyte of text is encrypted in 0.065 seconds, which is 22 times longer than using only 32-bit key, and this difference will keep growing with the message size. Taking into account all the pros solution we developed and improved the end-to-end encryption algorithm. The diagram describes the sender-server workflow, encryption and transmission on the message to server is shown on the slide. First, the session key are negated. The user writes a message, and when sending, it starts the process of the sending message block. Message key are generated by the sender and public key of the sender messenger, along with the recipient login, is signed by the sender's private key and encrypted with the session key and sent to server, where it's decrypted and its signature is checked by the sender private key. After confirming that the message is from the sender, the server prepares to receive the message and generate its own message key. Agree on the message key and encrypt the private key with this session key. Also, be recipient login his or her public keys is received and encrypted with the message key. Both the encrypted message public key and the recipient public key are sent to the sender's client, where the message public key is decrypted first, and then the recipient public key is decrypted after agreeing on the message key. The message is signed and decrypted with the agree user key, and then encrypted with the message key, which is sent to the server, where it is stored in the database with a symmetric message key. This slide describes the work of the receiver part, receiving and decryption this message. It also agrees on a symmetric session key that encrypts the message parameter of the server, which the user will use to select which messenger to decrypt or not all at once. After selection a messenger, the receive messenger block starts working. The messenger keys are generated by the recipient, and the public key of the recipient messenger, together with this message identifier, is signed by the sender's secret key and encryption with the session key, and sent to the server, where it is decrypted and its signature is verified with the sender's public session key. Therefore, the introduction of this algorithm provides a higher level of protection by encrypting each message with new keys, while session keys are used for public key. The algorithm also offers server owners to transfer the processing of decryption and encryption of large messengers to the client side by storing the key together with the messenger encryption in order to encrypt only it when transferring into the client and not the large messenger, which is much less process intensivity for the server. Thank you for your attention.